All right, so for business calculus today, we're going to work on two sample integrals. Both of them involve e to the x or some form like it. And this is because in section 13.2, a lot of the practical problems in business applications involving integration, it involves exponents or e to the x in particular. And so I want to do a couple of problems involved with integrating situations where we have an exponential in the integration. So the first one will be a mix of integration using exponents plus reminder of how to do integration by parts. So this is a simple question, a definite integral from 0 to 2 of x e to the x squared dx. That's a very simple question, okay? And so what we're going to do is we can see already that we can't just, we have two different functions here. Everybody see that? There's two different pieces to this function. We have this piece here and we have this piece here. So we cannot just jump to normal integration rules and say, well, that's x squared over 2 and that's e to the x squared. We can't do that. It's not going to work. So we need substitution. And the best thing when you have polynomials, x and x squared, is to let u equal the bigger of the two in terms of the degree of the polynomial, in this case, x squared. And then that means du will equal 2x dx, which means that dx is equal to du divided by 2x. So now as we go to substitute here, now I'm not gonna change the 0 and the 2. I'm gonna leave it undefined until we convert back to x squared and plug this back in. If you wanted to do it from just u, you would change this from 0 to 2 would become 0 to 4. But I'm not gonna mess with that. I'm gonna leave it like this. So x e to the u, so we're substituting u in for x squared, e to the u. And then dx, see, we have to substitute for dx. This we need to substitute, so that's du divided by 2x. So in our substitution, what's going to happen here, as you can see, these x's are going to cancel, but we're substituting this dx. We're putting this dx goes in there, and this dx is equal to this. So now we see that the x's will cancel. And this will leave us with the integral of e to the u du, all divided by 2. I'm going to pull that 1/2 out, though. Again, with integration, if you have a constant, you can pull the constant out in front of the integral. So no problem with that. Now I want to, again, if we were going to use u, we would have to convert 0 and 2 to be 0 to 4. We could do that. That's fine. So if we did that, we'd say, okay, I'm going to put 0 in here, 0 squared is 0. So this would be 0. And then if I put 2 in there, I get 2 squared, that's 4. It'd be 0 to 4. But I'm going to convert this back. I'm going to do 1/2 e to, sorry. I need to integrate it first. I get 1/2, the integral of e to the u du is e to the u. And now I'm going to convert it back. So this is 1/2 e to the x squared evaluated from 0 to 2. And so we have, remember this is f of, to capital F is the integral of small f. So this function, this f of x is equal to x e to the x squared. So capital F of x is, as we found, 1/2 e to the x squared. So if I take the derivative of this capital F of x, I get this again, right? And it's normally plus c, except for in this case, we have a definite integral, so we don't need some random constant. We're going to calculate it exactly. So this gives us 1/2 e to the 2 squared minus 1/2 e to the 0 squared. So in the end, we get 1/2 e to the 4th minus 1. And so you can put that in a calculator. I don't know what that'd be. E to the 4th, 3 to the 4, so it's like 80 divided by, it's about 40 probably, I'm just guessing. But you can leave it like this also. That would be a right fine answer. And so the way to integrate, so this is an integral using e to the x, but using substitution in order to be able to integrate this particular object. Now, let's go back over here. I mentioned this to you, but we have this capital F of x. That's the way you label the integral of a function. If I take the derivative of this, f prime of x, we get the derivative of the whole, so 1/2 e to the x squared times the derivative of the inside. So using the chain rule, the derivative of the inside here is the derivative of x squared, which is 2x. And we see here that 1/2 and 2, those will cancel out, or 1/2 of 2 is 1. So we wind up with x e to the x squared, which gives us our function back. So capital F of x, when I write it over here, f of 2, f of 0, that capital F, not small f, that gives us values for this. All right, so there's that. That's a simpler one. I want to do one a little more complex, again involving e. And this one is going to involve the span between, or the area between two graphs. We'll label them y, both of them y. This is similar to a problem we did in class, but we're going to have find the area between y equals e to the x and y equals minus e to the minus x. That's a bit complicated. And we're going to calculate this from 0 to 2. We'll do it that way. Now, the first thing we need to do is have an idea of what these two functions look like. Now, remember in the graphing strategy, there's a few things we can do. We can find f of 0 for both of them. And I think that's a great place to start. So f of 0 here, so f of 0 there would be e to the 0, which is 1. And f of 0 on this one would be minus e to the 0, which is equal to minus 1. So we know already at 0, we have two values here. We have 1 and minus 1. Now, the next question is, do we have any asymptotes? Well, we don't have vertical asymptotes here, but we do have horizontal asymptotes, because as x goes to infinity, this goes off into infinity this way, but as x goes minus infinity, this actually gets closer and closer to 0. And the opposite will take place here. As this goes to infinity, this goes to minus infinity, which is the 0. So we get minus from the negative side. This goes like this. So this is going to take off this way, and this is going to take off this way. Now, the other value that would be of interest to us is at 2. So if I check f of 2 for that first one, we get e to the 2. E to the 2, I don't know, 2.7 squared, so 3 squared is 9. So around 8, I would guess. So maybe something like that. And then f of 2 to the minus e to the minus 2 will give us some pretty small number. So it's going to be in here. So we have this area here bounded between these two curves. Everybody see that? We have these two curves. We're going to find the area here. This area here. It's the area between these two curves. And so what we need to do is take the integral then of the one on top. That's why we go to effort to graph it a bit, is just to get a feel for which one of these two are on top. If we make a mistake on that, at the end, we're going to get a negative number, which means we picked the wrong one, or we made a mistake. But in this case, e to the x is the one on top, minus, and then careful here, it's minus a minus e to the minus x dx from 0 to 2. All right, so we can split these integrals. We have the integral from 0 to 2 of e to the x dx. Very simple integration. Minus a minus is plus, so we have plus the integral of e to the minus x dx. So mostly this is not a challenge, but right here, we know the integral of e to the x. Sorry, that's still from 0 to 2. We know the integral from of e to the x, 0 to 2. This is the integral of e to the x is e to the x, evaluated from 0 to 2. But this one, we need to let u equal minus x. So that du equals minus, the derivative of x is 1, so minus 1 dx. So that means minus du equals dx. And we need that solved for dx so we can plug that back in. So this is going to be the integral. Actually, I'm going to leave it indefinite. And then I'll convert back. The integral of e to the u du, but there's a minus now. So now converting this back, so we have e to the x evaluated from 0 to 2 minus the integral of, we'll go ahead and integrate e to the u minus e to the u. I'm going to convert that, so that's e to the x from 0 to 2 minus e to the minus x from 0 to 2. So now we're ready to plug these things in. So we go back to these capital F's. So this is f of 2 minus f of 0. That will give us e to the 2 minus e to the 0, which is e to the 2 minus 1. That's that first piece, this piece here. And then the second piece, we have, so that's the first piece of it. The second piece, we have minus e to the minus 2 minus a minus e to the minus 0. That's that second piece. So that gives us a minus e to the minus 2 plus minus a minus. E to the minus 0 is 1. So what we see here is that we'll get, combine all this now. So we combine all this. Let's see. I'll put all that. Let's see if I can put it right here, okay? So we get all this, we get e squared minus 1 minus a minus e to the minus 2 plus 1. This will work out to e squared minus 1 plus e squared to the minus 2 minus 1. This is actually e to the second power plus e to the minus 2. That's our solution to that one. And that gives us the area bound by these two graphs. It's really, again, quite remarkable that these things produce such smooth and simple solutions. So the area between these two graphs is this. And the reason for doing these e to the x's again is that many of the financial problems, especially involving a string of payments or annuities with continuous payment or continuous interest, anytime we do that, compounded continuously or a stream of payments and we're compounding them instantly, these kinds of things, is you involve these exponents. And we saw this way back in the formula on compound interest and the difference between continuous versus compounded monthly or daily. But now we're going to sum up a stream of payments instead of just calculating a single value and saying, what is that value 10 years from now or 15 years from now? Instead, we have a stream of payments that we're going to compound continuously. And now we're going to sum all of those payments up and all of that interest up. And so we use a formula involving e to the x in order to sum up the value, the present value or future value of that sum of payments. And so you can see how if a company's trying to strategize what's the present value of a stream of payments compounded continuously at 3% or something along those lines, and summing all those up and the impact that would have in terms of calculating present value or there's another way of doing this in calculating future value. In other words, we get out 10 years from now, what is the value of that stream of payments when we get to the end of those 10 years? So it's looking both directions with this type of formula using e to the x. You're either determining in today's dollars what that stream of payments would be, present value, or you're asking the question, we get out 10 years from now, we got this stream of money, and now we want to go buy something with that stream of money. Say it's your kid's college fund or something, and you get out, you have a kid, you say, well, 18 years from now, we want to have X amount of dollars for them to be able to go to college. And so here's the stream of money we're going to save. And at that 18th year, here's what that value of money would be worth. And so we can do both of those. We'll talk about that in our next in-person lecture. But for today, just a reminder of how integrals involving e to the x work. And one was this integration by parts, integration by substitution, x e to the x squared dx. You can have problems like that in even some of these compounded present value, future value. And then also a look at what if we just take the difference between these two and the area between the two. All right, so that's our lecture for today. We'll see you guys at the next class period on Wednesday. And then I'll give you your take-home test, open book test, Wednesday. Don't forget you have those bonus problems. If you'd like to improve your grade a little bit, you can do those problems and you'll move your grade up to the next level. So if you currently have a B+, it'd give you an A-. You have a C-, it could give you a C. But you have to do all of the problems, show all your work. It may take a little bit. I think it may also be helpful for exam prep. Also, don't forget that you have some homework that you're supposed to be doing from chapters 12 and 13, the integration section of this. There's some review section questions that are due along with your test a week from today. All right, God bless you guys.